Hello, everybody. Welcome to I think it's our 17th SustainabiliTEA. Yep, I'm Kiralee.
And I'm Christina.
And we are very happy to host you today in this extremely interesting talk, which you are about to listen to. But while we wait for everybody to hook in and jump on, we will, of course, get ready with our cup of tea.
Yeah.
So, Christina, would you like some of this now? This tea, Christina, is made from leaves collected by the Nulul people up in the Dampier region, up in the northern of Australia. And apparently it can either put you to sleep or wake you up. I'm hoping for the latter.
Depending on what mood you're in.
That's right. So if your eyes start closing, just stop drinking.
Okay. Cool.
All right.
Nice. Smells really good.
Yeah.
Cheers.
So, cheers. Cheers. And cheers to everybody there. So we're going to make a start. And of course, I'm going to start off by acknowledging the traditional owners of this land, which are the Kaurna people, of course. And I'm also going to acknowledge that Tandanya here was a meeting place where a lot of knowledge sharing across various First Nations people took place. So communities like the Ngarrindjeri people from the south, the Paramount people in the Mount Lofty region, the Nukadu and Ngadjuri people from up north would have all, come across and shared knowledge in this land as well. And we acknowledge all these nations as well.
Cool, thanks for that.
All right.
All right, let's jump in. So today we're going to be talking to Dayne, and he will be presenting the mass timber case study at St. Luke's Health in Tasmania. This is an 8-story building with 6 levels featuring mass timber. This type of construction saw a 50% reduction in time to install compared to conventional construction, and the first carbon positive building in Tasmania. So welcome, Dayne, and please everybody get ready for a very informative presentation.
Fabulous.
Yeah, thank you so much. And then, of course, thank you for the honor of speaking at a great event. Hopefully everyone gets something from this. And as Ken warned me before, please, I'll try and keep it as quick as possible to 15 minutes and into a general chat. But no promises, there's a bit to get through. So I'll be as efficient as possible. So yeah, St. Luke's. St. Luke's is a fantastic project, the first carbon positive project in Tasmania, currently just finishing the base build in Launceston. So we'll start with a general project overview. So the project itself had quite a few complexities that we had to consider in the course of design. First, we had a heritage facade. So we had to retain the existing facade of the original building. This was part of the city requirements. So we had to figure out how this was going to be integrated into the design. The building itself is an 8-story building, just under 25 meters in height. We have level 1 and level 2, which is a traditional concrete post-tension structure. The reason for this was 2 reasons. Number one, it's on a floodplain in the middle of Launceston. So in the event of a 1 in 100 year, we are expecting high levels. And of course, we want to keep the timber safe for the 100+ years this building will be in effect. The other aspect was the architect had designed an internal staircase, which meant that we couldn't keep 1-floor compartmentation. So that means we had to go to a second level of concrete to get the fire requirements to work for separation between floors. Then we have levels 3 to 7, which is mass timber. It's glulam columns, glulam beams, and CLT floors. Level 6 is quite interesting because it also is an exposed balcony open to the elements. So we actually designed the timber concrete composite slab where we have the CLT floor, and then we engage the CLT floor with a concrete slab to help us get bigger loads in a bigger span to work in that area while providing long-term durability to the outdoor environment. and then for the steel structure to the roof, essentially. So basically the tallest columns, the double height columns you see on the outside of the building, and the roof structure itself is actually a steel frame structure cladded in Durability 1 hardwood. I believe it was a spotted gum hardwood we chose to clad the columns with. So in essence, the definition of a true hybrid building. Some of the highlights, which was mentioned before, was that the base build actually is going to take less than 12 months to complete. So the timber arrived on site in February this year. We started just after Christmas. Timber arrived in February, and we're due to hand over the base build of the building pre-Christmas. The CLT came from actually two separate, completely separate manufacturers in Australia, and the glulam was imported all the way from Germany. I'll talk a little bit about how we're able to coordinate that and how it worked. The timber structure, as mentioned previous, was constructed 50% quicker than concrete structure, the concrete structure equivalent. Essentially, because it's timber, we don't have any backpropping. We don't have to wait 28 days. We're essentially just putting together a big IKEA set of parts, which went together. And our tolerances for putting that set of parts together was 1/10 of a millimeter. So in a lot of areas where we're building in tolerances, thinking about how it went together, and that allowed for it to go together so quick and efficiently on site. From a sustainability point, 100% of the operational energy supplying this project is offset. And that's coming from a combination of solar panels on the roof and also by local renewable energy sources in Tasmania, which was a deal signed with the owner, St. Luke's, as a commitment to be a carbon positive project. And when we were calculating the building physics, the facade itself, we are achieving a 25% better energy efficiency than code requirements. So that had to do with the mechanical design, facade design, and the interfaces in the structure itself. One of the big things about the carbon reduction on this project was actually adaptive reuse. You know, how can we use existing materials which are there to form part of the story of the building? And the big part of that is the adaptive reuse of the existing facade. So it's a brick facade from the late 1800s. One of the other reasons why we had to really go with concrete as well was that we had to retain this facade. So we needed something to tie it back onto, which was much stiffer than timber. And so also helped us reduce a lot of our upfront carbon because we were keeping a natural material which was there anyways and not just using new material for the sake of it. The other big aspect as well, which helped with our carbon calculations and keeping it as carbon positive as possible, was not having any finishes on the inside. As you see from this image being shown, we're leaving the timber essentially exposed. We're able to achieve the fire safety requirements, the 90 FRL, so we don't have any suspended gypsum boards, we don't have any fire check linings. There will be some inner tenancy areas where we do have some internal linings and some glazing sections for meeting rooms, but generally all the floors are open plan and there's no requirement for any sort of fit out additionally to achieve the acoustics, fire, and of course keeping the aesthetics of the building that of a timber building. To give you an idea of our carbon calculations, so we actually achieved, there's two different ways that we were able to calculate this. So based on the Green Star aspect, we're able to achieve a carbon reduction of 28.8%. If we were to calculate it as per the zero carbon certification, which I believe is a future living calculation methodology, we achieved just short 59.3%, so just short of 60% carbon reduction on this building. Now, we did chart a way to go even further. For us to go really belts and braces on the project, which we really wanted to do to start with, would mean that, as you see here on the far side of the graph, we would have to look at more carbon neutral concrete, carbon reduced concrete, and these sort of elements. If we were to accept all of the options, then we would have achieved a 41.9% carbon reduction as per Green Star and or a 76.5% carbon reduction as per zero carbon certification. The only reason we didn't go down that road, well, there's two reasons really. First is we're building this in Tasmania. Tasmania certainly doesn't have the infrastructure like Adelaide, for example, Sydney, Melbourne. So getting carbon neutral concrete, which really means substituting Portland cement for fly ash, which is a waste product, is really more difficult and costly because we're having to ship it across the Tasman Sea, which I'm told is one of the most expensive shipping areas in the world, considering it's not that far. It is very expensive to get raw materials around to the batching plant to produce concrete. The other aspect is building in Tasmanian winter. If we were to look at using this sort of concrete, of course, we can play with the mix, but the builder was not, and us, we're not overly fond as engineers of going down that road, because it would mean likely that we would have increased curing times, which would also mean that the program would be affected in several different ways. So for us, we landed on what you see there, 28.8% carbon reduction as per Green Star, or 59.3% carbon reduction as per the zero carbon certification. I think it's important quickly to go through sort of the design process, because designing a timber building is almost very different, or almost completely different than a traditional method which architects, engineers would be used to. So our scope of works as the engineers on this project, we looked after the timber structural engineering. We assisted the client with the procurement strategy. Where were we going to get the timber from? How were we, what was the cost of that? We did the acoustic design for the project. We did the cost planning advice in collaboration with the cost planner and the builder, who was engaged under an ECI contractorship. We did the construction planning in collaboration with the ECI contractor. So we worked with them 6 months before ever getting on site, planning this project down to literally the nut and bolt. We did the technical report for the Tasmanian Fire Brigade to ultimately get approval to use mass timber in this sort of size and scale in the center of a city. And we also did the technical report for the insurance company, showing them how insuring a timber building in some ways is even less risk than traditional methods, and why they shouldn't be charging a premium to insure this type and building. We also did an LOD 400 model, and I'll explain what that is in a little bit, but essentially we were able to tell the builder exactly how many screws and nuts and bolts, and that's how we're able to get several different timber suppliers onto the project, because we did the model independent and were able to coordinate with the different producers around the world, and it all came together on site based on our model that we did independently. So the timber design process, as mentioned before, is slightly different. What we see traditionally here in Australian design ways, especially when predominantly Australian people are looking at the design process, is that you'll take it to a schematic design. So you'll get the rough size of the timber, you'll get an idea of what all the structural size of elements are, but there's still a lot of things that need to be considered. Mechanical needs to be considered, penetrations through beams, fire, acoustics. All of this has great impact on timber procurement and the cost. So traditionally, this is where a lot of what we see in the market, a lot of Australian engineering firms would say, now you need to engage with the supply chain, and we'll let a producer finish the design. For us, we find that a bit backwards. It's a bit like getting a concrete company to finish your slab design. Their job is to sell timber. Their job is to produce elements, and we feel it's down to us to really take the design to a true 100%. And that's what we did. We stayed the course with the design team all the way through to construction documentation, and that allowed the builder to go to the market much more traditionally, like they would to go get their windows or their concrete or their rebar supply. It made it much more cost advantageous, because there was a real tender, there was a real life tender that everyone was going on a like-for-like basis. The design was 100% done, so we eliminated a lot of the contingencies, 90% of the contingencies, and then we also worked with them to put them in contact with a specialist installer, which mitigated the rest of the contingencies, because we found a specialist carpentry installer who was able to take the full risk and contract for the install and management of the coordination, right from the offsite holding yard, getting it to site, and then installing it. So for us, that's how we went about this project, taking risk off the table, working with the full design team to understand not just the structure as an engineer, but all of the peripheral things that influence the architecture and the performance of the building. For us, we went down the journey to start with all different types of timber systems. I mean, this building ended up being glulam and CLT, but we explored a lot of things, lightweight cassettes, hybrid systems, timber concrete composites, which you see on level 6 that we did. We looked at LVL options. We looked at glulam floors and glulam columns, CLT floors, CLT walls in areas. So we really went through an exploratory phase to figure out what were the right products to meet the aesthetic want, the structural want, and of course the cost plan. We had to do, because Tasmania can be quite wet and similar across Australia, this is something Europeans, we really don't think about a lot, is humidity, torrential rain, really cold aspects. And we had to think about, okay, what is the moisture content going to be inside this environment? So, building in the winter can have its difficulties, and we had to make sure we were designing the building so that it could get wet, that it wasn't a delicate thing that had to be covered, and then we had big delays on the construction site. We designed the building so that during the course of construction, it could go up to service class 2. We can get moisture content up to 20%, and the team could still carry on building this building. And we had to work to make sure the mechanical designer long-term kept the building internally in that service class environment, that it wasn't too humid, and that, there was a lot of good ventilation and good supply of air. The fire design is, of course, super important. And this is something that we had to go through to get authority approval. We work with WSP fire engineers on this, and we did a lot of the finite element analysis of the connections. So for us, we had to establish first what was the FRL, the time equivalency calculations. We had to make sure that we had compartmentation. So essentially each level is separated. So if we get a fire, for example, on level 3, that fire will not spread to level 2 or level 4. It'll stay contained in that area for 90 minutes, which gives a lot of time for the local fire brigade to get to site and to put out the fire. And it also means that the broader building is not affected. The building will not collapse, which was also a big topic for the insurance companies. And then we had to think about, okay, in the event of a fire, how do we repair elements? How do we go about this? And we put a plan in place for that to happen. In this area, we didn't require any encapsulation, so we didn't require any fire check because of the compartmentation, the size of the building, where our exits were, and some areas that were concrete, like concrete cores, for example. But there is instances in other buildings that we've designed where we do have to encapsulate some areas, but in this instance, nothing had to be done. We wanted to make sure the timber products that we specified were tested to AS standards and met the local codes. We even looked at the adhesives. What glues were we using in the CLT to make sure that we were achieving auto extinguishment? We had to look at the species selected. What, is it a softwood? Is it a hardwood? That changes our calculation methods, and it changes the size of the timber. So all of these things had to be considered. And once we get into that, then we get into the finite detail. For us, you see on the right there, that is one of the details that we come up with. So the dotted red line you see there against the CLT and the glulam columns, that's indicating the char lines. So we're showing the authorities, and we're showing the design team, and we're showing the carpenter on site that in the event of a fire, there's going to be timber left over. So the timber will burn from the soffit and the side of the columns, and it will only burn to that line after 90 minutes. We're expecting in our finite time equivalency that the fire would actually only last about 60 minutes at peak. So we would never actually get to a full 90-minute fire. So that means that we had a safety factor there to achieve and make sure that the building would always stand up. On the picture there on the left, that's some testing that we've done previously with other glulam suppliers internationally to show you exactly what it would look like in the event of a fire. So that's our design on the top right. And then in the event of a fire, that's the representation of what it would look like after the fire. And as you see there, the connectors are protected. The building will not fall down. Essentially, the timber is acting as an insulator to protect the steel or aluminium connectors. Acoustic design. So very quickly, we went through figuring out what were the requirements, the L&D factors, the vibration performance. How were we going to get services through? How does this affect the floor-to-floor ratio? So especially early in concepts, we had to work with the architect to figure out these strategies and the performance requirements. We ended up designing a 150 millimeter raised floor system that gave us discontinuous construction on top of the CLT floor, which meant that we can keep the 55 decibel requirements for the building from an acoustic performance, but it also gave us enough room to reticulate and provide maximum flexibility for low-level services, GPOs, data points, because we really wanted to be a flexible space. We wanted the future tenants over the next 50 to 100 years to have ample flexibility, not have to think too much about these sort of things. Long-term future-proofing of the structure, essentially. MEP service reticulation was the big one for us. When we're looking particularly at the mechanical aspects, we had to think about penetrations. Penetrations, a lot of times, depending on the size of the ducts, can dictate the depth of the beam, not just the span that is going. So we engaged with the MEP designer early, and our mandate was that it cannot be a D&C contract. You know, we cannot wait for this to be figured out by a contractor, you know, a year later. So their mandate from day one was, we're doing this as a full detailed design. We need to know exactly where it's going. We need to work with you to coordinate these penetrations. And we actually went as far as, again, future-proofing. We figured out what were the penetrations needed today, but then we also cut in other penetrations and concealed them along the beam so that in the event, you know, the next tenant in 20 years' time require more penetrations, there's additional penetrations there that they can open up and use. But this was a big thing for us, this sort of level of reticulation, strategy, and coordination between the architect, us as the engineers, and the mechanical designers. And then working with the architect, there's a lot of things architecturally, especially when you're going to leave the timber building exposed, that you must consider. So for us, we had to look at the timber species. What was the best species for CLT and glulam on the project so that the architect was happy that it looks appropriate, but also keep within the budget of the project? We had to think about the feasibility. We had to think about the timber species. Does this limit our procurement? Do we look at 100% Australian species, or are we going to be forced to look at international procurement options because of procurement timeframes, because of cost, because of a variety of different factors? What's the timber grade and quality required? I mean, do we want to see knots in the timber? Do we want to embrace more of an industrial visible look? Or do we want it to look more like a finished countertop where you don't see any knots whatsoever and just the grains? This has very different architectural impressions. And of course, costs associated with this. This project ended up going with more of a industrial visible. We wanted to be an economic timber. We wanted to see the knots, and the architect wanted to embrace it being a timber building. They wanted to see slight imperfections. They wanted to see knots. They wanted to see a slight discoloration. And that also leads to the last point. You know, you cannot think about a timber building. What does it look like tomorrow when it's done? You have to think about what it's going to look like in 20, 30, 40 years' time. Do we need to provide UV protection to the timber over time to stop discoloration? Or is the architect happy for the timber to age naturally and gracefully over time and tell a story? In this instance, Terroir, the architects for this project, wanted to tell a story. They wanted to, in 100 years' time, people to look back and know that it was a 100-year building like what was done generations before us. They didn't want to, superimpose a strict maintenance regime on the project to make it looking like fresh timber every year, which has a cost associated with it. So again, they went for more of the industrial visible look, and they wanted it to tell a story over time. The benefits on site are a big thing, especially when you're cost planning, but also when you're considering it. So as mentioned previously, 50% quicker installation on site. Reduction of costs and weight. So this structure was put together with only 8 to 10 carpenters on site. And because the timber components were made in a factory in Australia and also in Germany, there was no waste on site. Literally, there was zero waste through the structure here, which is a huge cost saving and also helps with our carbon calculations. It's a lighter structure. So the timber structure itself is 50% lighter than a traditional concrete structure. So there was significant savings in foundations and foundation loads and core design. The timber's left exposed, as mentioned before, so we didn't have all of this gypsum and paint budget that we had to think about in the base build. But also, we don't have a maintenance regime over time. You know, a person with a 20-year tenancy doesn't have to come in and get everything repainted. We're keeping the building in its raw form. So dramatic savings there in terms of the fit out as well. And easy construction. We're dealing with very lightweight structural components, which required a much lighter crane than, say, if we're looking at a precast aspect or post-tension cables and things like this. So again, a lot of efficiencies on site, which obviously kept us in budget, but also allowed us to deliver this building in less than a year's time from a base build perspective. Here's a short video for us. So as part of the key having an ECI contractor on board, and as part of our responsibility for LOD 400 modeling, we actually worked with Fair Brothers, the builder, to create a whole construction plan. So we actually sat down with them. So this is our LOD 400 level of one level. And so we sat down with them and figured out, okay, where are you putting the crane? Where do you want to start? Where should we start installation? Because this actually was how we numbered the members. And this then went to a construction management plan. So the carpenters at everyone's site knew exactly which element went first, which element went second, third, fourth, and so on and so forth. It really helped us to micromanage on site. It helped us to coordinate our transportation. So the factory in Germany knew which beams to press first. The CLT factory, both in Aubrey Wodonga, Exlam, and Cusp in northwest Tasmania, knew which elements to make first, second, third, and how to arrive on site. And this is why we're able to achieve that 50% reduction in time, because essentially it's putting together an IKEA set of parts. We've left nothing unthought about, which also meant that the builder can take away a lot of their contingencies, which was the case. Their first cost plan was well over budget. But once we started working with them and they started understanding timber, and we really started working with them to understand how it goes together and how simple it is compared to some other construction methodologies, they were, much more confident. Durability. Of course, when you're dealing with timber, you have to think of durability. We want this building to last for more than 100 years. So we had to think about termites. We had to think about humidity, density, fungal attacks, mold, contact with the ground, corrosion of fasteners, you name it. We've had to think about it in our design. But again, this is part of a timber building, very different than concrete. But again, it's just something we had to consider in our species selection and our connection specifications. DFMA, as I mentioned before, LOD 400 model. This is some exits of some of my model. And as you can see there, we're really putting in the top right section up in this region here, you can see the shear connector, which is connecting the timber column to the timber beam. We've actually modeled it into our model, and we've actually modeled in the screws that connect those elements together and the dowels that connect those elements together. We've modeled in some angle brackets. We've modeled in screws. We've modeled in, you name it, we've modeled it. So as part of it, this model then goes to the different producers around the world, and they can produce their different sections and products out of this model. It also gave the builder flexibility. They didn't have to go to just one CLT manufacturer to finish the design. In theory, we designed this building for radiata pine because the mandate for the project was as much local as possible. So CLT comes from Australia, but we couldn't get unfortunately, we really wanted a glulam manufacturer from Australia, but we couldn't get it in the right lead time. They had about a year's lead time at the time when we approached them for this project. So then we had to go to Germany to get it. But it also gave us complete flexibility. We went to 6 glulam suppliers to get a price, and they found they were able to have much more ability in negotiation because the design was 100%, and they knew it was a project ready to go. But for us, this was the big key, is coordination inside the design team, not leaving it to producers to then design, because as a producer, they're only going to think about the elements from a production perspective and maybe not consider all the other elements like the acoustics, surface reticulation, fire, all those other elements. So we wanted to take as much risk off the table as possible. And then we go into fabrication. Those elements go into a shop drawing. and then they produce, well, this is the CLT, for example. They press it together, and then from our LOD 400 model, it's being read. Each element is being read by a computer around the world, and we have a computer cutting the components for our project, all coming together millimeter perfect. Very minimal human interface. It's all being built by robots. So again, the degree of the model has to be accurate, and we have to really coordinate with the design team, all the penetrations, where everything's going, and really leave no stone unturned in the planning process. So workshop wrap up. So yeah, just for us, that's the sort of project, that's the sort of process we did. As mentioned before, we had two amazing CLT producers, Xlam out of Albury Wodonga, for the majority of the project. They did 90%, and then the top penthouse was actually done by Cusp in northwest Tasmania, who did the first ever CLT out of eucalyptus nitens. And then, as we said, unfortunately, we couldn't get a local glulam supplier, so the glulam come from Germany. But for us, a great project. We're working on several more at the moment, but I guess this just gives you a taste of what it's like to go through a timber design workshop.
That's great, Dayne.
Yeah.
It was so informative.
Wow.
I just learned so much.
Yeah.
Really amazing.
What a fantastic project, Dayne.
Yeah.
That's fantastic. We're just going to go to see some questions now, Dayne. And she's just asked St. Luke's, is this the client? What class of building is this?
Yeah, great question. So St. Luke's is the client, yeah, and it's an office building. I apologize, my Australianisms isn't up to code. So is that a class 5, I think, or class 9? Class 5, yeah, exactly. Yeah, so it's class 5. So the tower itself is a class 5, and then the first level is actually it's the entranceway, but it also has a cafe restaurant. So it's a bit of mixed use on the ground floor plane, but the tower itself is an office building. Yeah.
In the event of a fire, how do you go about reinstating the charred layer post fire?
Yeah, great question. So there's two ways to do it, essentially. So we can either take back the timber, so you can take back the char layer back to a raw timber finish and then re-glue on additional safety layers, because it's only held together with a poly-based adhesive, so you could re-glue it. Or the other thing, because it's held together with literally the screws are holding together the floor, nothing more. So in a project in Germany, what we did previously is we actually backpropped the floor, and we were able to remove a whole panel and then put a whole new panel back into place. Similar to a column, right? We would prop the beams on the other side and release the column and go from there. But yeah, it's much simpler. I would say it's more carpentry work than anything else. It just depends on the extent of the fire and how much the damage is that's caused.
Yeah, excellent. And here's one from Nick.
Nick just talking about the seismic ductility. Well, essentially, we didn't require any of the engagement of the external bracing. So the architect itself actually put this into a competition without any engineer's input. So they put it in thinking, oh yeah, they'll need it, we'll add it in because it looks great and we'll definitely need some stability. But when we looked at calculating the core, we're actually able to get it stiff enough that we didn't require any of the bracing itself externally. So they're actually only held together with 3 screws, top and bottom. So yeah, no requirement. All of the lateral forces are going back through the core itself.
That's amazing. I just have a follow-up question on the fire with the charred timber. So that's assuming none of the actual structural components are getting affected, and it's just kind of the cladding or lining that's charring, and then you just replace those. Is that right?
Yeah, exactly. So just on that image there, in our design image, so they're all structural elements. They're all load-bearing structural elements. And then the red dotted red line is dictating the predicted depth of charring after 90 minutes. So basically, in the event of a fire, it'll char to that point and no more, but we'll still have enough meat on the bone, shall they say, enough timber there to still support the structure. Again, fire loads are different than normal loads. We would have to look at re-strengthening for sure, because we need more to increase the load of a normal building, normal office load. But in the event of a fire, certainly nothing will collapse. It'll deflect more than traditional, but it won't fall down.
That's really quite amazing.
Just showing people how to use the raised hand function. um, but I did have a question, though, Dane. So thanks heaps for raising so many things to think about. But I wondered if you could share some of the interesting conversations that you might have had with the fire brigade to kind of get them on the over the line to be okay with the timber structure.
Yeah, for sure. Great question. And this is a conversation we have with a lot of authorities, not just in Launceston, but of course, Sydney, Melbourne, Adelaide. The big thing for us was showing them that we were not considering the building, let's say, from a holistic point of view. You know, they weren't so concerned about travel distances and where the sprinklers were going and this sort of thing. They wanted, I guess, proof and calculation that what we were doing was safe and above code. Luckily, one of our colleagues, Dr. Michael Klippel, who works with us and at ETH in Zurich, he's actually one of the drafting members of the Eurocode 5. So there's two ways we calculate this building. Of course, there's the AS standards for engineering, the timber code, but a lot of CLT and other aspects, we derive some of the factors and thought processes from Eurocode 5. And with that, we're able to do advanced modeling. So the charring factor is one thing, but when we were looking at the connections in particular, we were able to do finite element analysis to say, okay, in the event of a fire, in our computer program, this is the kilojoules of energy, this is the temperature, which is going to be around that. And then we were able to show that actually how the temperature doesn't get to the connector, and the connector will stay there. And because it's advanced modeling on the basis of code, they were willing to accept it. And so we just were able to show them calculations and images and models of how this was going to be safe. This is something that in the past I've seen doesn't go great when you go to these sort of to authorities like this and you're just talking about, in theory, a charring factor or something. It is much more complex than that, and it needs to be considered as such. So it's just really getting confidence, knowing that we were thinking about it more than just holistically. We were getting down to the finite elements and really doing a lot of calculations.
That's really cool. So I guess from a technical point of view, that would fall under an alternative solution. So
yeah, exactly.
I think that kind of follows on to my next question, which is who drove the idea of using CLT as the main structural elements? Was it the client, or was it the architect and engineers, or like how? Because as an architect, we find it really difficult to get clients on board to use CLT, because there's all these we spoke about before, there's all these unknown factors and they don't want to take the risk, right? So if it's already coming from the client, then that's a bonus, but usually that's not the case.
No, in this instance, it was from the top down. So St. Luke's Health, being a health organization, you know, this is their new headquarters. And so when it went to competition with Terroir, the mandate in the competition was they want a fully sustainable, healthy building. And naturally, those words, the architect went to timber, and then we were brought on board after the competition was won. So right from there, they wanted maximum carbon reduction within the budget as possible. They wanted to use biophilic and healthy building elements. Timber naturally sits in that. And then, of course, we had a budget to meet. Like everyone else, while they had big aspirations, we had to prove to them that we could do it within budget. So that's why we really went through a lot of cost planning and planning of construction, because we really wanted to eliminate a lot of contingencies. The first cost plan that come back from the contractors were well over budget, but the client had faith in us, design team, that we could work with them to alleviate a lot of their fears. They had never done anything like this before. And we brought on the right people to assist them from a subcontractor perspective. We started getting quotes out from the market and quickly realized that we actually brought it in budget and slightly less. So in this instance, it came from the top down. That was our mandate. And the key things were, of course, budget 1, carbon 2, and healthy environment 3 were the things that really for them were non-negotiable, which is, I would say, unique. Usually in the event of anything, feasibility is always number 1, and then carbon, I'd like it, but if I can't get budget, then let's just go back to what we know. But this was never the case. They stand the test of time for over a year as we designed the building.
Dayne, I'm just a little curious. I'm assuming that the wood would have to be treated with something to prevent a lot of the issues that you had on one of your slides, you know, mold and termites and all that sort of stuff. How can you explain a little about that?
Yeah, for sure. So the treatment itself, actually, because it's suspended 2 levels in the air, and with Tasmania actually doesn't have termites, we didn't have to treat the timber from an H3 perspective or anything like this. But what we did is we specified a treatment coming from factory. So what we wanted to do was have a water-resistant treatment applied to the timber to keep the UV stable and to be water resistant for the first couple of years on site. So as we're building and as we're getting it into a locked environment, but then moving forward, the timber is actually not treated at all. It's a raw treatment in itself. Having said that, in other applications, absolutely, you're right. I mean, if we were looking at exposed timber columns, you know, we'd either be looking at a durability 1 timber, like a super hardwood, a spotted gum or a merbau for termite, or we'd be looking at chemically treating timber like H3 or something like this. So, but in this instance, we didn't have to do it because it's stuck in a service class 1 environment internally, and we're above ground and out of the wet. So.
Oh, that's great. Yeah, because I was just thinking from a wellness perspective, that's great then. Yeah, for the people in the office.
Yeah.
It was the budget equivalent to concrete/steel building? That's the question.
Yeah, the findings with the debrief from the builder, my understanding was that it actually comes in slightly better. So it was forecasted to be slightly more expensive, but once we realized the site foundations were significantly less, so there's a big savings in the ground because 50% lighter. It was put together 50% quicker. So like you say, how often do you build an 8-story building in less than a year? So that's huge savings over the course of many weeks and prelims. There's only 8 to 10 people on site putting together the structure. So less site sheds, less accommodation required. The tower crane is only working on this thing. There was only 1 delivery in the morning and 1 delivery in the afternoon. So we didn't have these layers of complexities that you would normally get with a normal building. And it's hybrid. So we had 2 floors of concrete anyways, which would have been on par with the normal concrete building. So for us, we found that it was actually slightly better. But once you take into considerations the full global time consumption, and the developer considered the quick return. I mean, they were forecasting to have to pay, I believe, on the money for 18 months until they got the building, and they're getting it less than a year. So there's a savings there of over 6 months from the developer perspective that they can work into their feasibility because tenants are already taking spots.
Yeah, so they're getting an income a lot quicker than they would.
Yeah, much quicker. Yeah. But the biggest thing in the cost planning here is, you know, the argument is always timber's more expensive than concrete. I agree. I 100% agree with that comment and that idea. But if you leave timber exposed, as we were able to do in this design, then we need the budget. We need the gypsum budget. We need the ceiling budget. We need the paint budget because it is a finished element. And so you're not comparing apples to apples, just concrete to timber. That's apples to oranges. You have to think about it from a full cost plan 3 level. It really is going down the whole 50 elements and really chopping and changing and transferring budgets because timber can encapsulate so much more of a budget than just a raw structure.
Yeah, that's a really good point. It's not really apples and oranges. Cool. All right. I think we need to wrap up the session, but thanks everyone for joining. That was a really good conversation, and thank you so much, Dayne. That was really great experience learning about St. Luke's.
Yeah, it's a fabulous topic. Fabulous. And this is our last SustainabiliTEA for 2023. So we hope everyone has a great rest of year. And we look forward to seeing you in 2024.
Yeah. And please keep us updated on the completion of St. Luke's, because I think everyone who's interested to kind of see the finished product in its full glory.
Yep, very much.
Yeah, absolutely. Happy to share pictures with Ken and the team, and you can share it on the social media platforms you guys have. And thank you so much for the honor for today. It's been a pleasure.